class.
Okay.
Welcome.
Yes.
Welcome. Please turn off your microphones. Please turn off your microphones. Thank you.
Doctor, do you hear me, please? Doctor,
I'm Mariam Amir Mazlagani, Associate Professor of Artificial Intelligence Group in Department of Computer Engineering of Amerikabi University of Technology. In this part, we focus on probability and random variables, and we expect that you will be more familiar with these concepts, probability, random variables, statistical analysis at the end of this part of engineering mathematics course. But what's the content of this part? First of all, we discuss about probability. Then we discuss about random variables. We introduce PMF, probability mass functions, CDF, PDF. Do you have my point? Do you have the red point? Do you have my pointer?
Yes, yes, yes,
Yes,
clear.
doctor.
Okay.
Yes, Doctor.
Yes, okay. Then we discuss about some important PDF, probability density functions. Then we discuss about some important PMF. Next, we discuss about functions of random variables. We have a random variables, and we want now and obtain some information about functions of a random variable. Then we talk about expectation and then moments. Then we start our discussion about two random variables. We discuss about joint PDF, joint PMF, joint CDF, and correlation, orthogonality, and independence of random variables. The reference of this part are these two books. The first book is Random Variables and Stochastic Process by Populis. The main material of these slides are from this reference or reference A. But this reference is almost complicated. Maybe it's difficult for you to read this reference. So I suggest you that focus on my slides and my explanations, and then you can use the second reference. This reference, Theory and Problems of Probability, Random Variables, and Random Processes. It's an easy reference for your study, and it contains many solved problems that you can use these solved problems and be more familiar with the concept of these parts. Uh, uh, you should consider that your exam is at this date and your exam is in person. It's very important. Please consider that the student doesn't attend the exam, grade will be 0. So you should plan to participate in this exam in person at this date. Okay, let's start the subjects. First of all, we want to discuss about probability. And at first, we discuss about random experiment. What is a random experiment? A random experiment is an experiment that we don't know the result of that experiment before doing that experiment. For example, rolling a dice. Before roll a dice, we don't know the result of this experiment. Or suppose tossing a coin. Before doing this experiment, we don't know the result of this experiment. Such experiments are random experiments. Random experiments are the experiment that before doing them, we don't know the result of that experiment. Another concept, another definition, sample space. What is a sample space? Sample space is related to random experiment. When we are faced with random experiments, we encounter sample space. What's the meaning of sample space? Sample space is the set of all possible outcomes of a random experiment. All possible outcomes, all possible results of a random experiment. For example, in rolling a dice, the sample space in rolling a dice, if we use this symbol omega for sample space, omega is 1, 2, 3, 4, 5, and 6. Yes, sample space is this set. Set of all possible outcomes of that experiment is our sample space. Or in tossing a coin, or sample space is heads and tails. So I think now it's clear what's the meaning of random experiment and what's the meaning of sample space of the random experiment. But another definition about event. What is an event in a random experiment? Event is related to random experiment. Any subset of sample space is an event. For example, in rolling a dice, A set A that is equal to 1 is an event. Or B, for example, in rolling a dice, please suppose rolling a dice, B 1, 2, 3 is an event. Or in tossing a coin, H is an event, or T tails is an event. So any subset of sample space is an event. For example, event A, event B, and so on. Any question? So in this slide, we discuss about random experiment, an experiment that we don't know the outcome of that experiment. Before doing that, what's the meaning of sample space? Sample space is the set of all outcomes, all possible outcomes of a random experiment, and event. Any subset of sample space is an event. Okay. Next slide. When we are faced with a random experiments, we should talk about probability of different events. The probability that are assigned to different events should satisfy some conditions. The conditions are listed here. First of all, probability of events. A is an event. A is an event. Probability of the events should be non-negative. The probability should be positive or 0. Second condition, probability of sample space. Omega is used for sample space. Probability of sample space is equal to 1. It's clear that the probability of sample space is equal to 1. And the third condition that the probabilities should satisfy is this condition. If we have two events such as A and B that are disjoint event. What's the meaning of disjoint event? It means that the event that their intersection is empty. If we have two events, A and B, that are disjoint, that their intersection is empty, then the probability of union of A and B is equal to probability of A plus probability of B. These three conditions are called Kolmogorov conditions, the probabilities that we are assigned to the outcomes of a random experiment should satisfy these three conditions. Any question? Probability should be non-negative. Probability of sample space is equal to 1, and if we have two disjoint events, the probability of their union is equal to the summation of their probabilities. Okay. Please consider that if we have these three conditions for probability, it's not need that we also mention that probability of A should be less than 1 or equal to 1, because the second condition and third condition resolves this. We know that the probability is between 0, and 1. But three conditions result that the probability of any event should be less than 1 or equal to 1. Okay, okay. I try to speak slowly. Any question? So the probability of events should be non-negative. The probability of sample space should be equal to 1. And if we have two disjoint events, then the probability of the union of these events is equal to the summation of the probabilities of A and B. Yes, we have these three conditions, and the condition that the probability of A should be less than 1, equal or less than 1 is resulted from these three conditions. Okay, next slide. This slide is very important. In this slide, we talk about conditional probability. What's the meaning of conditional probability? For example, probability of event A given M. It means that if we know that the event M we have the event M and event M is occurred, then what's the probability of event A? Given event M, what's the probability of event A? Given M, what's the probability of A? For example, in rolling a dice, uh, assume A is 1 and B is 1, 2, and 3. It means that if we know that probability of A given B means that if we know that B has been happened, what's the probability of A? I repeat, if we know that the B has been happened, what's the probability of A? This is the meaning of probability of A given B, or probability of A conditioned on B. We know that B has been happened. What's the probability of A? Okay, let's discuss about the formula of conditional probability. Probability of A condition M is equal to this fraction. In the numerator, we have probability of A intersection with M, and in the denominator, we have probability of M. In this example, we have probability of intersection of A and B, that is 1, divided by probability of M, probability of B, that is 1, 2, 3. In this example, the conditional probability of A given B is equal to this fraction. So this formula is very important in statistical analysis. Probability of A given M is equal to probability of intersection of A and M divided by probability of M. Any question? Let's talk about the probability of sample space given M. Omega is a symbol that is used for sample space. What's the probability of sample space given M? Okay, we use the formula for conditional probability. We have probability of omega intersection with M divided by probability of M. Can you say me the intersection of omega and M? intersection of a sample space and an event M. What's the intersection of omega, that is our sample space, and an event M?
It is the event of M.
Yes, yes. Thank you. It's M. Because omega is all of our sample space, all of our sample space. M, as defined before, M is a subset of omega. So if we intersect a subset of omega with omega, the intersection is M. So we have P, probability of M divided by probability of M, that is equal to 1. So the probability of sample space condition to any event is equal to 1. Okay, any question? But what is this formula? We know that probability of B given A is equal to this. What we should write in this space?
Probability of A.
Yes, thanks. Probability of A. We know that from this formula, we have this formula. Probability of B given A is equal to probability of intersection of A and B divided by probability of A. Okay, so from this formula, we have probability of A intersection with B is equal to probability of B. That's right. Probability. From this formula, we have this formula. Okay. Uh, this formula is similar to this formula. Just we use A, B instead of A intersection with B. This notation is used in the probability theorem when we write probability of A, B. It means that probability of intersection of A and B. So probability of intersection of A and B is equal to probability of A times probability of B given A. So it's not a new formula. It's a reformulation of the first formula. Okay, but we can extend and generalize this formula, and we can obtain some formula that is very important for us. For example, probability of A, B, and C. Probability of A, B, and C. It means that the probability of A intersection with B intersection with C. It means this probability is equal to probability of A, probability of B given A, probability of C given A and B. We can prove this formula very simply. We now want to prove that probability of A, B, and C is equal to probability of A, probability of B given A, and probability of C given A and B. We want to prove this formula. We start with writing the meaning of this probability. Probability A, we write the definition of probability B given A. What's the formula of this conditional probability? Please help me. Probability B conditioned A or given B is equal to what I should write in this place. Probability B given A is equal to probability of A intersection with B divided by probability of A. And also we write this formula. probability of intersection of C, A, and B. Divided by what? What I should write in this place?
Probability A intersection with B.
Thank you. Yes. Probability of the condition, or condition here is A and B. So the probability of A and B, or A intersection with B. Now we can simplify this formula. You can see that the two sides of this equation is equal. So we prove this formulation for the probability of A, B, and C, or intersection of three events A, B, and C. Any question? Okay. Now we can generalize this formula for a more general case. Please consider this formula: probability of A1, A2, to AN. We have n events here, and we want the probability of intersection of these n events, A1, A2, to AN. We can use the above formula and extend that formula for this case. This formula is equal to probability of A1, probability of A2 given A1, probability of A3 given A1 and A2, until probability of AN given A1, A2 to AN minus 1. Okay. You can simply prove these formula. The way of proving this formula is completely similar to the way that we prove this formula. We prove this formula here. You can prove this formula in a similar way. Okay? It means that you replace the formula for conditional probabilities and simplify the formulation to prove this equation. This equation is called chain rule. Chain rule. This formula is called chain rules for probabilities, and it's very important. Any question? Okay, so we review the conditional probability. We said that probability of an event A given B is equal to probability of intersection of them divided by probability of conditions, means in a B. Then we introduce the chain rule. We discuss about chain rule. The probability of intersection of n events is equal to probability of A1, probability of A2, conditioned N1, continued probability of AN given A1, A2, AN minus 1. Okay, any question? This chain rule is very important in many statistical analysis. Okay. Let's go to the next slide.
Here's my doctor.
Okay.
Assalamu alaikum.
Salam alaikum.
Doctor, already we're talking about the probability. My question, at first the lecture you say about the day that go to get the exam. So if you don't mind, already all this lecture we go to add it with the other lectures to be get it in the exam, or is this different? In the last this month, 26th for July, January, no?
Yes. Your exam is in 26th January or 7 Bahman, and it's in person. You have 2 parts for this exam: linear algebra.
Yes. It means this added with the linear algebra?
and probability.
In a few days. It's a lot of, you know that, doctor.
Yes,
Why? I don't know why.
I
It's fast
understand.
and a
I
lot of
understand.
lectures, and we have another lectures, and we
I
have the language
understand
about.
you.
Let's
I
say I'm
understand you.
studying. You
I
think this is
understand you.
easy? I think no. I think no.
You are
Thank you so
right.
much. I
You are right.
apologize, but I think we need some solution. Help us, not make it all a lot of lectures in the same in a few days. This is a problem, big problem. Doctor, sorry if I take from your time. Thank you so much.
You are right. I understand you. You are right. But our duty is teaching you these concepts, and I hope that I can do my duty well. Don't worry, please. Consider the subjects and follow the course. If you can follow the course, you can have a good exam, inshallah. Any question? Okay. Let's start the next slide. This slide is about total probability theorem. This theorem also is very important in statistical analysis. But what's this theorem? This theorem is this formula. A is an event, Bi for I from 1 to M are some events. So A, B1, B2, to BM are some events. But what are B1, B2, and BM? They are the partitions of sample space. What's the meaning of partitions of sample space? It means that suppose this set is our sample space omega. This set is our sample space omega. We partition the sample space to some parts. We call these parts B1, B2, B3, B4 to Bm. These parts, B1 to Bm, are disjoint. It means that the intersection of Bi and Bj is empty. And also, the union of B1 to Bm
Equal 1.
is equal to sample space. So, if we have BIs that satisfy these two conditions, the intersections of Bi and Bj for I, intersection of Bi and Bj is empty, and also the union of B1 to Bm is equal to sample space, then we said that B1 to Bm are partitions of are partitions of omega. So, is it clear the definition of these partitions B1, B2 to Bm? Any question about the definition of B1, B2 to Bm?
Sorry, doctor, can you repeat the first step?
Yes, yes. I said that in this slide we want to speak about total probability theorem. This theorem needs the meaning of partitioning of a set. What's the meaning of partitioning of a set? Our set here is our sample space omega. or sample space omega is this red rectangular. If we partition this set to some parts that the intersection of the different parts is empty, and also the union of all partitions B1, B2 to Bm is equal to or sample space or omega, we said that we partitioned omega to B1, B2 to Bm. So, is it clear the meaning of partitioning a set, here partitioning the sample space? Is it clear the meaning of B1, B2 to Bm? Okay,
Yes, doctor, it's clear.
okay. Let's continue. Let's continue about this formula. What's the meaning of this formula? This formula said us that the probability of A is equal to the summation of probability of A conditioned or given Bi times probability of Bi. But what's the application of this formula? You imagine that we know the probability of event A given Bi, and we need the probability of A. Then we can use this formula. I repeat, when you have the conditional probability of A conditioned on some partitions, and you have the probability of A without any conditions, you should think of a total probability theorem. Okay, this is the application of this formula. When, I repeat, when you have the conditional probability of A and you want the probability of A without any conditions, you should think of total probability theorem. This is the application of this formula. But let's talk about the proof of this formula. What's the proof of this formula? If any question, please. Now we want to prove the formula. We have this formula and we want to prove this. Okay. Let's start with the first side. We have this equation. Is this correct? I write probability of A is equal to probability of A intersection with omega. We know that A is a subset of omega, so the intersection of A and omega, that is our sample space, omega is our sample space, is A.
It is right.
Okay, is it clear? Probability of A intersection with sample space is equal to probability of A, because the intersection of any event with sample space is equal to that event. Is it clear? Any question? Okay. Now we should relate this formula with Bi, that are the partitions of our sample space. So we can write omega as this. Is this okay? We mentioned that the union of B1 to Bm is equal to omega. So in this formula, we replaced omega with this. Okay.
Okay, continue, doctor.
Okay. And from the rules of sets, we have this equation.
Good afternoon, doctor.
Good afternoon.
Excuse me, for a couple minutes, your voice wasn't clear.
Okay,
I,
do you
I
have my voice?
now,
Do you
yeah,
have
I
my
have it.
voice? Yes, okay, okay.
I would like to ask you some questions about the final exam. I think, or maybe I understand wrong. Is it in the Persian language?
No, it's in English language.
Ah, good. First thing, we are so glad to see you and hear you today, and we hope to see you maybe in the future.
I hope to
Uh,
see you too.
Thank
Okay.
you. And we are, to be honest with you, we are afraid and we are confused also because, the short time that we have, and we are looking for your support.
Yes, I said that you are right and I understand you, but let's continue the subject so we can cover the contents of this part. Okay. From the rules of set, we have this equation. A intersection with union of B1 to Bm is equal to a union of A intersection with B1, A intersection with B2, to A intersection with Bm. It's from the rule of sets. Okay. Then uh, please consider these events or these sets A intersection with B1, A intersection with B2, A intersection with Bm. We said that, we mentioned that intersection of Bi and Bj is empty. So the intersection of these sets are empty too, because the intersection of Bi and Bj are empty. So the intersection of these sets are uh, empty. For example, we called A intersection with B1 as M1, A intersection with B2 as M2, and A intersection with Bm as MM. We said that Mi intersection with Mj is empty. So Mi and Mj are disjoint. When we have disjoint events, as we mentioned in these slides, when the intersection of two events is empty, then the probability of union of these sets is equal to the summation of their probabilities. So here we have M1, M2 to MM, that their intersection is empty. So the probability of union of them is equal to probability of M1 plus probability of M2 to probability of MM. And then please consider what's M1. M1 is intersection of A and B1. So these probabilities, we use this formula. Please consider. Here we have the probability of M1, that means the probability of A intersection with B1. Probability of A intersection but B1 is equal to probability of A given Bi times probability of Bi. So we have this formula. So we use the formula that we have discussed about them before, and we proved total probability theorem. You see that we start with probability of A, and then we obtained this formula that is equal to these summations. So we prove the total probability formula. Please repeat the steps that we do this proof, and if you have any questions in any step, please ask me.
Sorry, doctor. Can you take one example and solve it?
Yes, I can. Suppose that we have two classes, class 1 and class 2. Probability of error condition class 1 is given to us, that's equal to and probability of error given class 2 given us probability of class 1 is equal to and probability of class 2 is equal to the question is the probability of error without any conditions. What's the probability of error without any conditions? Please consider that we have two classes, for example, two classes in a classification task. We know the error of our class or classifier conditioned on class 1 is equal to the probability of error conditioned on class 1 is equal to 0.4, and probability of error given class 2 is equal to this value. Probability of two classes, class 1 and class 2, is given to us, and we should compute the probability of error without any conditions. Here we have the conditional probability and we have the probability without any conditions. I said that in this situation we think of total probability theorem. So we use total probability theorem, and we said that probability of error is equal to probability of error and we replace the values in these parts. Any question about this example? I should mention that these subjects that I talk about them in this class is related to our BSc courses. We have a probability and stochastic courses in BSc, and the students pass this course in BSc. So when you are MSc or PhD students, you should be familiar with these concepts, and these are elementary concepts in probability and statistics. You should consider this point. Okay, any question? Yes, in this example, Mr. Nureddin, do you mean in this example or the proof of total probability theorem? Do you mean this example? Okay. In this example, we have the probability of error given class 1 and given class 2. And we want the probability of error without any conditions. So in this situation, we use a total probability theorem. Total probability theorem tell us that probability of error is equal to probability of error conditioned on class 1 times probability of class 1 plus probability of error given class 2 times probability of class 2. And we only replace the values that this example give us. Probability of error given class 1 here. Probability of class 1 here. Probability of error given class 2 here. Probability of class 2 here. Okay. Okay, let's back to the slides. Here you are. Now, I said that in this slide we talk about total probability theorem. We discuss about this formula, we prove this formula one, and we talk about the applications of this formula. Any question about total probability theorem? The proof of formula is very important. You should know this proof exactly. Okay, any question? Let's go to the next slide. This slide is about Bayes' theorem. Also, this theorem is very important. I select the more important topics for you because our time is limited and we should cover important topics. Bayes' theorem is very important. What's the Bayes' theorem? Bayes' theorem is this formula. As you see, it talks about the probability of event beta conditioned or given event A. You can see that this formula can simply be obtained from the formula of conditional probability. Please consider probability of beta conditioned of on A, given A. We use this formula and we write it's equal to probability of beta intersection A divided by probability of A. Now, but we should obtain this formula. How we can obtain this formula from this? In this formula, we have a probability of intersection of beta and A in numerator, but in this formula, we have probability of A given beta times probability of beta. We know that probability of beta intersection with A, we can have this formula. We have this formula, this simple conditional probability formula. So, from this equation, we know that probability of A intersection of B is the multiplication of these two terms. Probability of A given beta times probability of beta divided by probability of A. So we simply prove this formula. When we use Bayes' theorem, when we use Bayes' formula, you can see that when we have probability of A given beta, but we want probability of beta given A. In this situation, we use the Bayes theorem. Is it clear? In a conditional probability, when we want to switch the events A and beta, we should use the Bayes theorem. In other words, when we have the probability of A conditioned on beta, but we want the probability of beta conditioned on A, we use Bayes theorem. We want to switch the A and beta in this condition. Is it clear for you? I think the proof is very simple, but the application of this formula, is it clear for you? When we have the probability of A condition beta, but we want the probability of beta given A, we use Bayes formula. Bayes formula is very important. Bayesian method means that they use Bayes formula. Perhaps you know the Bayesian methods in different fields. Bayesian methods usually use Bayes theorem, this theorem that you can see in this slide. Okay, any question? Any question? Okay, let's continue. What is this formula? If you compare these two formula, you can see that the numerator is equal, but the denominator is different. PA, in this formula, we have this equation instead of P probability of A. Why is correct? Is it correct? Can you say why we can replace probability of A with this summation? Is the probability of A equal to this summation?
Total probability theorem.
Yes,
Why?
it is the same.
Why
Why?
PA is equal to
Numerator, because the numerator equal to numerator and the denominator equal to denominator.
yes, please explain for me why the denominator is equal to this. Why? My question is this. Why PA is equal to these summations? Why? Why this equation
شلون راح احكي؟
is correct?
According to probability theorem. Theo-
Yes, very good. Mr. Al-Abidi,
ميتم.
according total probability theorem, it's completely correct. We talk about total probability theorem in details. And here we only use total probability theorem. We use this formula instead of probability of A. Why? Because of total probability theorem. We know that probability of A is equal to these summations. Okay. This is a different form of Bayes theorem. We can use this form or this form for Bayes theorem. In Bayes theorem, the denominator is the summation of the numerator, as you can see in this formula. But let's have an example. Again, suppose that we have two classes, class 1 and class 2. We know the probability of error conditioned on class 1. For example, and we know the probability of error conditioned on class 2. And we also know the probability of class 1 and probability of class 2. Now what we want? We want the probability of class 2 condition to error, given error. It means that if we know that we have error, what's the probability of class 2? We want to compute this probability. We said that if we have the probability of error conditioned on class 2 and we want the switch probability of A and class 2, we want to switch these two events and we want the probability of class 2 given error, we should think of Bayes theorem. And we use Bayes theorem here. So we have probability of error condition class 2. We have probability of error condition class 2. Probability of class 2. But what's the probability of error? We want the probability of error 2. So for probability of error, as we mentioned in this formula, we use total probability theorem. So we have probability of error, total probability theorem. Probability of error condition class 1, probability of class 1, probability of error class 2. By replacing these values in this fraction, we can obtain probability of class 2 conditioned error. And it means that if we know that we have error, what's the probability of class 2? In the same way, we can compute probability of class 1 condition error. Okay. Any question? Okay.
Excuse me, doctor. Doctor, you hear me? Sorry.
Yes, here you are.
Yeah, thank you. Already we check that everything when you go to Epsilon, and if you don't mind, can I ask you? I have some feeling, afraid. I can't understand very well. Is this normally, or the and what is cause of that? You have answer if I say you give me or submit the lecture in the fast. This is the first time I see that. So apologize. Not it's mean have a problem from your side. No, but just I have some feeling. I understand everything very well. So it is normally for this lectures, or you can explain me how can I go to studying or getting by a few in a few this few days. So if you have some support or help me, please tell me. Thank you so much.
Okay. I said that these subjects are related to our BSc courses. So we expect that you are familiar with these subjects. Also, I start with basic concepts. For example, I started with random experiments, sample space, events, and I continue the subjects. So I expect that you can follow the subjects of these slides. I don't know how many students feel such as you.
Yes, I understand that. So you explain some law and take examination for each one, and also there was not just the law for that. You understand what I mean? Yeah, and you take this lecture fast. I apologize. Not it's mean the problem with you. And I'm sorry if I cut that about the other student. I apologize for him also. But I told you about me. In
Okay,
my
okay,
idea,
okay,
if you ask me this question and gave him the time, I think all of them go to talk or give you that. I don't know. Maybe the message and that lectures you can't get it. I apologize, but you are the best, and I know you have
okay.
the information. Thank you so much.
You can ask your questions everywhere you don't understand. I hope that my explanations is
Thank
whole is useful for you.
Thank you so much. You are the best. I understand you want to give out the lecture with the more information, but the problem we get it the yes we get it that and the baccalaureate ESV and without duration. This is the problem, and already you have idea, not idea. You have that lecture. It's very good talking, and we need slowly and give me the time to ask. This only the problem maybe. We have to make it get more information from you. Thank you so much, Doctor.
Okay, okay. Thanks. Okay, if you have any questions from the beginning of these sessions until now, you can ask me from these slides, from this slide, this slide, or this slide. Okay, I repeat the example. In this example, we want to be more familiar with the applications of Bayes' theorem. We have two classes, class 1 and class 2. We are faced with a classifier. This classifier should distinguish between these classes, should classify the examples in these two classes, class 1 and class 2. We have the probability of error given class 1 and also the probability of error given class 2. Also, we have the probability of class 1 and class 2. What we want the probability of, for example, class 2 given error. It means that we know that the error has been occurred. We have error. Now we know that we have error. What's the probability of class 2? It is the meaning of this conditional probability of class 2 if we know that we have error. So we know the probability of error given class 2 and we want the probability of class 2 given error. In such situation, we should think of Bayes' theorem. We use Bayes' theorem. What's Bayes' theorem? We introduced Bayes' theorem in this formula, so we use this formula. We rewrite Bayes' formula for this problem. It's equal to probability of error given class 2 and this formula. We have this formula. Now, we want to replace the values in these parts. Probability of error condition class 2, we have this value. Probability of class 2, we have this value. But in the denominator, we have probability of error, and we don't have probability of error. The problem doesn't give us the probability of error. So we should compute the probability of error. How we should compute the probability of error? We know the probability of error condition of class 1 and also condition of class 2. And we want the probability of error without any condition. In such situation, we should think of total probability theorem. So we use total probability theorem. Here we rewrite the total probability theorem for this example. Probability of error condition class 1 and so on. And we use this formula in the numerator of this fraction. Is it okay? Any question? If you need more explanation, please Please say to me. Okay. I review the subjects, and if you have any question, please ask me. In this slide, we define random experiment, sample space, and events. If anyone have any questions, please ask me about random experiment, sample space, and event. No question. Next slide. In this slide, we talked about the conditions that probabilities should satisfy. If any question, please ask. No question. In this slide, we talked about conditional probability. What's the meaning of conditional probability? Probability of A given M means that we know that M happened, and when M happened, we now want the probability of event A. We want the probability of A given M. And we also discuss about the chain rule problem, that is the results of the conditional probability formula. If you have any question, ask please. No question. In this slide, we talked about total probability theorem. We discussed in details of this formula, and we said that when we know the probability of A conditioned on some partitions, or if we have the conditional probability of A and we want the probability of A without any conditions, we should think of a total probability theorem, and we should use this formula. And also we prove this formula. Here we prove total probability theorem. Any question?
Sorry, doctor.
Here you are.
In this subject, we mean that A is subset from B.
No. I explain for you now. In total probability theorem, total probability theorem.
Sorry, doctor, but I mean that A is event from the
Yes.
omega, that the subset of, the summation of B.
Yes, I explain for you. Please consider. We have this sample space omega, and we partitioned it to B1, B2 to Bm. And what's A? It's an important question. Thanks for your question. A is a subset of omega. A is a subset of omega. Okay. A is an event. So A is a subset of omega. This picture can help you to understand the total probability theorem better. Is it okay?
Okay, doctor. So we mean that we application. Okay, mama. As applied this, we can see the A is the transmission of the B.
No, A is a subset of omega. A is an event.
I understand this, but I mean A is event when
Yes.
B is occurs.
Like
Like this.
Bi are the partitions of omega. Bi's are partitions of or sample space omega, and A is an event. A is an event, and Bi's are partitions of omega, as you can see in this picture. So A may have intersection with some BIs and it may have no intersections with other BIs. A is a event. Okay.
Okay, thank you. That's clear. Thank you.
Okay. Here you are. Okay. I said that this is the proof of total probability theorem. After total probability theorem, we talked about Bayes theorem. We said that it's a very important theorem. Bayes rule is a very important rule, and we discussed about this formula, and we said that when we have probability of A given beta, and we want the probability of beta given A, in such situation, we should think of Bayes theorem, and we should use this formula that is equal to this formula too. Any question about Bayes theorem?
Sorry, doctor. This
Okay.
rules or this theorem, we applied on discrete random value, or variable, or the continuous.
Okay, here we speak about random experiment and we speak about events. In the next slides, we discuss about random variables. Here we discuss about A and B car. A and B car are events, are some events. Okay? We talk about random experiments and we now don't talk about random variables. We have some events, A, B car, and so on. Okay? In the following slides, we talk about random variables, discrete random variables, continuous random variables, and so on. Okay?
Okay, doctor.
Any question? Okay. Mr. Jabbar asked when we use Bayes theorem. When we have probability of A conditioned on beta, and we want probability of beta given A, it means that we should switch the probability of A and B in this conditional probability. We should think of Bayes theorem. Please consider this example. In this example,
Excuse me, sir. If I have another class such as C3, I add this class with this probability.
yes, you may have more classes. It makes no difference. For example, C1, C2, and C3. We know probability of error condition of C1, for example, probability of error condition on C2, for example. And we also know the probability of we know these informations and we know these values. What we want probability of class 3 condition on error. It means that we know that we have error. We want to compute the probability of class 3. In such situation, we should think of Bayes theorem because we switch error and class 3 here. And we have this formula from Bayes formulation. We replace these values from here, this value from here, but in the denominator we need probability of error. How we can compute the probability of error? Could anyone said me?
By using a total probability.
Yes, okay, thank you very much. By using the total probability, because we know the probability of error condition of C1, C2, and C3, and we want the probability of error without any condition. In such situation, we should think of total probability theorem. So it's equal to, is it okay? Any question? Any question?
Thank, thank you, Doctor. It's clear.
You're welcome. Okay. Uh, and the last subject of this session, independent event. What are the independent events? We have two events, A and B. When or two events A and B are independent. What's the meaning of independent? It means that they are not related to each other. A and B are not related to each other. In formulation, A and B, two events such as A and B are independent if we have this formula. It means that the probability of intersection of A and B is equal to the multiplication of their probability, probability of A times probability of B. If we have these equations for two events A and B, then we said that these two events are independent. It means that they are not related to each other. It's better to not use separated. Independent, they are not related to each other. They are irrelevant to each other. It's better to use these words, these independent events, irrelevant events, or unrelated events. You can see that if we have these equations for two events A and B, if we have probability of intersection of A and B is equal to the probability of A times probability of B, we can compute the conditional probability of A given B. We know that from the conditional probability formulation, we know that it's equal to probability of intersection of A and B divided by probability of B. We replace this formula here and is equal to probability of B, probability of A. It's very important. You should consider that if A and B are independent, probability of A given B is equal to probability of A. And we expect this equation because we said that A and B are not related to each other. So knowing B is not effective on probability of A. Knowing B has no effect on probability on event A. So the probability of A given B is equal to probability of A. This is the meaning that the two events A and B are independent of each other. And you can simply, in the similar way, prove that probability of B conditioned A is equal to probability of B. Why? Because A and B are independent. They are not related to each other. So it's important to keep in mind that if probability of intersection of two events is equal to the multiplications of their probability, then we said that these two events, A and B, are independent from each other. And we have this formula for independent events. Any question? Yes, you can use this formula. This is the definition of two independent events. A and B are two independent events if we have this formula for them. And we don't prove this formula, but we can see that if we have these equations, then the probability of A condition B is equal to probability of A. That means that A is not related to B. That means that A is independent of B. And also probability of B given A is equal to probability of B. It means that B is not related to A. B and A are independent. Yes. Any question?
Can you repeat, doctor, please?
Yes, of course. In these slides, we defined two independent events. We said that two events A and B are independent if we have this formula for them. If probability of A intersection with B is equal to the multiplication of probability of A and probability of B, then A and B are independent. When we have this formula, we can simply prove that probability of A given B is equal to probability of A. Here we proved this. And we also simply, in the similar way, can prove that probability of B given A is equal to probability of B. What's the meaning of probability of B given A is the probability of B? It means that knowing A has no information about B. It means that A is not related to B. It means that A is independent of B. Okay? We defined two independent events by this formula, and we use this formula to obtain these two new equations. Okay, any question? Okay, I think it's enough for now, and the following slides for the next sessions, inshallah. Please read and study the subjects of these slides and repeat them for yourself.
We appreciate your kindness, doctor.
Here you are. Any questions? Yes, for exam, for the final exam, you should know the proof of the theorem. For example, the proof of Bayes theorem, the proof of total probability theorem. Of course, the proof of theorems that we explained in the class. If you continue with the class and you understand the class, you will have no problem for the exam. Okay, thank you.
Good day.
Thank you, doctor. Thank you so much.
Thank you. في أمان الله.
في أمان الله. Have a good day.
في أمان الله.